Okay, we're going to start by looking at an example. Did you ever wonder what salary the president of your college or university earns per year? The Chronicle of Higher Education conducted surveys in 2010 and 11 to examine the question. The table examines whether the president earned $400,000 or more in total compensation for public and private universities and colleges, and you see the data spelled out there in the chart. So we've got presidents of public universities or private universities or college, and then we have those divided up by those who earned less than $400,000 or those who earned $400,000 or more. At the bottom, you see the totals for the columns, and at the far right, you see the totals for the rows. 718 indicates how many people were surveyed total. Okay, this is just the chart again, so we don't have to flip back and forth. We're going to let A be the event earned less than $400,000, and we're going to let B be the event public university president. We're going to find the probability of A, the probability of A prime or not A, the probability of B, and the probability of B prime. Okay, now you may want to go ahead and take a stab at this, and if you do, pause the recording and do it, and then resume the recording to check your answer. The probability of A, remember, A is the event earned less than $400,000. There were a total of 351 of those surveyed that earned less than $400,000 out of a total of 718. So we just put 351 over 718, and that gives us 0.489. The probability that they did not earn less than $400,000, that they instead earned $400,000 or more, well, there were 367 that earned $400,000 or more over 718 total, and that gives us 0.511. Now we're going to look at B, the probability that they were a public university president. So there were a total of 199 public university presidents out of 718, and dividing that gives us 0.277. And then there were 519 that were not public university presidents. So 519 over 718 gives us 0.723. Now that should have been pretty familiar. Hopefully you didn't have a lot of trouble with those. But suppose we want to know the probability that a public university president earns less than $400,000. Well, from the table, there were 199 public university presidents, and 102 of them earned less than $400,000. So we'll do 102 over 199, which is 0.5126. For this, we were focusing only on the row of public university presidents because that was the assumption that they were already a public university president and then that they earned less than $400,000. So it's not the same as the probability of making less than $400,000 because, again, we're just narrowing it down to those that are presidents of public universities. And that is our condition that we're using as our baseline. So we've reduced the sample space from all the presidents surveyed to just those from a public university. What we found in this example is the probability that a person earns less than $400,000 given the fact that they are the president of a public university. This is called a conditional probability. It's the conditional probability that A will occur given the fact that B has already occurred. The conditional probability that they will earn less than $400,000 given the fact that they are the president of a public university. The symbolism looks like this. It's P, and then you got your parentheses. There's a vertical slash separating A and B, and you read it, the probability of A given B. Conditional probability is pretty easy to determine from a table. You focus on the row or column that deals with the given fact. For example, what we just did, we completely narrowed down our focus to the row of public university presidents. But when the information is not organized in a table, it's really helpful to have a formula to figure it out. So here's our formula. The probability that A will happen given that B has is the number of elements in the intersection of A and B divided by the number of elements in B. Let's try an example. We're going to use the information at the beginning of the section, which I've recopied here, to find some more probabilities. We're going to find the probability of A given that B does not occur. We're going to find the probability of B given A and the probability of not B given not A. And just a reminder, A represents the fact that they have a salary less than $400,000, and B represents the fact that they are the president of a public university. Okay, again, you can use the chart for this, and it shouldn't be too difficult. Why don't you pause the recording and give it a try, and then resume to check your answer. Okay, first of all, the probability of A given that B has not occurred or given not B. It's the probability of earning less than $400,000 given that the president is not a public university. In other words, is a private university or college president. So the intersection of A and not B is 249, and the number of those in not B, the number of those that are the private university presidents was 519, so 249 over 519 gives us 0.4798. The probability of B given A, the probability that you are the president of a public university given the fact that you make less than $400,000. So we're reducing the sample space to A. We're going to find the intersection of A and B, which is 102, and then we're going to find the number in A, which is 351. 102 over 351 is 0.2906. And then finally, we're going to find the probability that you make $400,000 or more given that you are the president of a private college or university. So again, the intersection is 270, and the number of those that are private college or university professors, or presidents rather, is 367, and that gives us 0.7357. We can also use Venn diagrams to illustrate conditional probability problems. Here's a Venn diagram with A and B filled in. The intersection is 0.1421, and then we've got 0.3468 that's only in A and not in B at all, and 0.1351 that's only in B and not in A. Remember, we can find those by subtraction. Now, what we can do to find the probability of B given A is we're going to focus on A because we're given that A has occurred. And we're going to take the ratio of the number that is part of B that's contained in A, in other words, the intersection, which is 0.1421, and we're going to divide it by the total number that's in A, which means we're going to add those two numbers together and get 0.4889. So we have 0.1421 over 0.4889, and we get about 0.2907. Now, this might be a little bit different because of rounding. This example. You're given the probability of E, F, and the union of E and F, and you want to find the probability of E given F. Why don't you pause the recording and give this a try, and then resume the recording to check your answer. Okay, so we're going to find the intersection first, and we're going to use the addition rule to do that. We know the union, and we know the individual probabilities. So the probability of the union is the probability of E plus probability F minus their intersection. So 0.7 equals 0.4 plus 0.5 minus the intersection. Do a little algebra and we find that the intersection is 0.2. So we're going to go to our Venn diagram and we're going to put 0.2 in the intersection. We're going to subtract that from 0.4 to get that 0.2 is in E alone. And then we're going to subtract that from 0.5 to get that there's 0.3 in F alone. Now we can figure out the probability of E given F. So we're going to focus on F. The intersection is 0.2, so that goes on top, and the probability of F together is 0.5. So we have 0.2 over 0.5, which is 2/5 or 0.4. Here's another example. Give the recording a pause, try it out, and then resume the recording to check your answer. Okay, so we have two fair coins that are tossed, and at least one was ahead. At least one means either 1 or 2. Find the probability that both were heads. So our sample space has 4 likely outcomes. You can have heads, 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 tails, tails, heads, or tails, tails. remember, it kind of helps to think of the coins as maybe being two different colors so that you can get that heads and tails, and then tails and heads is actually two different outcomes. Okay, so our event is at least one head, which would be either heads, 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 tails, or tails, heads. So there's three ways that can happen. Event 2 is going to be two heads, because that's what we're trying to find the probability of. We're trying to find the probability that both were heads. We're given E1, we want to find E2. So in other words, we're figuring out what's the probability that E2 occurs given that E1 has occurred. Really, there's only one way that this can happen. There's three ways that we can have one head. There's only one way out of that two heads can occur, so it's really just common sense tells us it's 1 out of 3. You could also use the definition. You could find the intersection, which is 1 out of 4, and you could find the probability of event 1, which is 3 out of 4, and it also gives you 1/3. Now, little word of warning, it's important not to confuse the probability of A given B with the probability of B given A. And I just clipped this from the book because I like the example they use. In a criminal trial, a prosecutor may point out to the jury that the probability of the defendant's DNA profile matching that of a sample taken at the scene of the crime, given that the defendant is innocent, is very small. In other words, if you're really innocent, given that fact, the probability that we're going to find your DNA is small. That's what they say. What the jury must decide, however, is not that. It's the probability that the defendant is innocent given the fact that the DNA matches. And it's really two different things. It says it's sometimes called the prosecutor's fallacy. In 1990 conviction of a rape suspect in England was overturned by a panel of judges who ordered a retrial because the fallacy made the original trial unfair. This mistake is also called confusion of the inverse. So they're really two different things. The probability of A given B and B given A are not the same. The probabilities are not going to be the same. And there may be some cases where they are, but by and large it's not. So we need to really be careful and not just say, well, it doesn't matter, it's the same thing. It does matter, and it is not the same thing. Okay, so we have a product rule. If the probability of E is not 0 and the probability of F is not 0, then the definition of conditional probability shows that the probability of E given F is the probability of the intersection of E and F over the probability of F, and the probability of F given E is the probability of F intersect with E over the probability of E. Kind of easy to confuse. If you look at it though, the given is always the one on the bottom. The top is always the intersection, and it really doesn't matter if you do the intersection of E and F or F and E, it's the same thing. So the top is always going to be the intersection of the two, it doesn't matter what order. The bottom is always going to be the probability of the given. So it's the probability of the intersection over the probability of the given. And let's see, here it says that if E and F are events, then the intersection of E and F may be found by either of these formulas. So there's two ways. If you need to know the intersection, there's two ways you can find it. You can find the probability of F times the probability of E given F, or the probability of E given, or times the probability of F given E. And again, notice that the probability, the individual probability always matches that of the given. So what they did is they solved the little formulas we did a minute ago for the intersection, and you got these two options. This is just the way that I mentioned a minute ago of remembering which goes with which, although these should be on your formula sheet, so I don't know if that's going to be a real stress for you, but notice that the given is always matching the individual probability. Okay, here's another example. Why don't you pause the recording and try this, and then resume the recording to see how you did. Okay, we have, according to data from U.S. Census Bureau, we can estimate the probability that a business is female-owned as 0.28. We can 0.282. We can also estimate the probability that a female-owned business has 1 to 4 employees as 0.504. What is the probability that a business is female-owned and has 1 to 4 employees? Okay, so what we know is we know the probability that it's female owned. We know the probability that it has 1 to 4 employees given that it is owned by a female. Now we want to find the intersection. So we're going to use that formula we just used. We're going to multiply the probability that the business is female owned. We're going to multiply it by the given, by the fact that it has 1 to 4 employees given that it's owned by a female. And that's going to give us our intersection, which is 0.142. Okay, let's read through this example. It actually goes on to another slide. It's kind of a long one, but try to hang in there with me. You might want to take some notes as you go through it. So you got a company, they need to hire a new director of advertising, and you've got either person A or person B. They're both assistant advertising directors for the major competitor. They do research, and they find that neither A or B both managed campaigns at the same time. So they're individual things here. They find that A is in charge of twice as many campaigns as B. Also, A's campaigns have yielded satisfactory results 3 out of 4 times, while B's have yielded satisfactory results 2 out of 5 times. Suppose one of the competitor's advertising campaigns is selected. All right, we can represent this situation as follows. Let A denote the person A does the job, and B will be the person B does the job. S will be satisfactory results, U will be unsatisfactory. Then the given information can be summarized by a probability tree, which we'll see in a minute. A does twice as many jobs as B. So the probability that you pick a job that A has done is 2 out of 3, while the probability that you pick a job that B has done is 1 out of 3, because A does twice as many as B. So that's going to be the first stage of the branches. You know, whether you pick A or B, it's 2/3 to pick A, 1/3 probability to pick B. Then from those, you're going to branch off into satisfactory versus unsatisfactory. A is satisfactory 3/4 of the time, and unsatisfactory 1/4. B is satisfactory 2/5 of the time, and unsatisfactory 3/5. We've got the 2/3 for picking A, and then the 3/4 satisfactory, 1/4 unsatisfactory. The 1/3 of a chance of picking B, 2/5 satisfactory, 3/5 unsatisfactory. And then what we do to get the probability for each of these branches, like to get the probability that you pick a satisfactory job done by A, you're going to multiply the branches together. So 2/3 times 3/4 is 1/2. So you have a 1/2 of 50% chance of randomly picking a campaign that was done by A and done satisfactorily. You have a 1/6 chance of picking a campaign done by A and done unsatisfactorily. And then you can see for B, the chance of picking B where he's done a satisfactory job is 2/15, and B where he's done an unsatisfactory job is 1/5. And notice if you add all these fractions up, these final fractions, you get a total of 1, which is what you should get because probabilities always total 100%. So we're going to find the probability that A is in charge of a campaign that produces satisfactory results. So in other words, we want the intersection. What's the probability that you have A and that it's satisfactory? And we know that when A does the job, the probability of success is 3/4. The probability that's satisfactory given that A is done is 3/4. By the product rule, we get 1/2. In other words, it's what we got on the branch of the tree. So if you do the tree and you set it up, then the branch just gives you what you're looking for, at least as far as this one goes. The probability that B runs a campaign that produces satisfactory results. Again, you're going to really just multiply those two tree branches. You get 2/15. There's your probability. Probability that the selected campaign is satisfactory. Okay, so for this one, we want to collect the satisfactory events. And so we just kind of go down those final totals and we pick the ones where it didn't matter whether A or B did it, the results were satisfactory. And we have 1/2 and 2/15, and we add them together and get 19/30. What's the probability that it's unsatisfactory? You actually have two choices here. You can take what we just got in C and subtract it from 1, or you can add up the other two branches. Either way, you get 11/30. And then E, find the probability that either A runs the campaign or the results are satisfactory, or possibly both. All right, so to find, that's what we call a union. So we're going to, event A combines branches 1 and 2. Event S combines branches 1 and 3. So we're going to add up 1, 2, and 3, and we get 4/5. And here's another example. And again, you're going to want to try to build a tree on this. So suppose 6 potential jurors remain in a jury pool. 2 are to be selected to sit in the jury for the trial. The races of the 6 potential jurors are 1 Hispanic, 3 Caucasian, and 2 African American. If we select 1 juror at a time, find the probability that 1 Caucasian and 1 African American are drawn. All right, so what you're going to need to do is you're going to need to create a tree, but instead of 2 branches, we're going to have 3. You're going to have 1 for each race. You're going to have, and then you're going to pick 2 from that. So you're going to have 2 sets. Give it, pause the recording, give this a try, see if you can set up the tree, and resume the recording to check your answer. Okay, so we're going to show the tree. They use C to represent selecting a Caucasian, A for selecting an African American. Okay, so here's what our tree is going to look like. What you got to remember is we're starting with 6 jury members. Once we pick 1, we're down to 5. And then we'll have to account for who gets picked. So our first choice is either going to be Caucasian, African American, or Hispanic. The probabilities, there were 3 out of 6 Caucasian, so 1/2. There were 2 out of 6 African Americans, so 1/3, and 1 out of 6 Hispanic. So that's how we set that up. Now focus on the first choice being Caucasian. If the first juror chosen was Caucasian, now we're down to 5 jurors, and only 2 are in the jury are Caucasian now because we've already picked the one out. So you have to adjust the probabilities accordingly. So notice the difference in the fractions there. If we pick African American first, then again, notice the denominators on our second choice are all 5. The African American, though, has been reduced by 1 because you've already picked 1. And then finally, the Hispanic, you'll notice we're completely missing that on the last one because there was only 1 member to begin with of the jury that was Hispanic. So that branch is totally gone. That possibility is totally gone in the second choice. All right, if you multiply them through and you see a couple of them have already been done, here we've got the probability that you pick a Caucasian and then an African American is 1/5, and then probability under 4 here is the probability that you pick an African American and then a Caucasian in that order. And again, the order is important here because you're reducing by 1 every time you choose. So on the first draw here, this kind of explains it. We wanted to find the probability of selecting exactly 1 Caucasian and exactly 1 African American. So that's going to be those 2 branches that were worked out. We got the probability for both of those. And what you're going to be doing is you're going to multiply those together and you get 1/5. All right, another example. 2 cards are drawn without replacement from an ordinary deck. Find the probability that the first card is a heart and the second is red. Okay, pause the recording, give it a try, and resume the recording to check your answer. Okay, again, we can use a probability tree. We've got one drawn here. You might want to refer to the deck of cards. There is one on your formula sheet. We're going to draw 2 cards without replacement. So the probability that the first card is red, is a heart, and the second card is red. So our first choice is a heart. So we split into heart and not heart. We have a 1 in 4 chance of drawing a heart and a 3/4 chance of drawing any other card. Now, here's the deal though. Our card deck has now gone from 52 to 51. So our second choice is going to be out of 51. And then we split it up between red and black. Well, the heart is red. So we've already pulled a red card out of there. So now it's down to 25 over 51. And then there would be 26 black cards left out of 51. The reason they didn't bother finishing in the lower half is because all we're concerned about is drawing a heart and a red. And we're going to multiply those 2 together. So 1/4 times 25 over 51 is 25 over 204, or 0.123. Now we're going to draw 3 cards without replacement, and we want the probability that exactly 2 are red. Pause the recording, give this a try, and resume to check your answer. Okay, first choice, red. And this is actually in one sense pretty easy because it's either red or black. The non-replacement is really important to remember. So our first choice, we have 26 out of 52 red, 26 out of 52 black. The second choice, we have to do red and black for each of those two branches. So we've got 25 over 51. If we've already pulled a red, 26 over 51 for black. And then notice the black, if we chose a black first, we have a 26 over 51 probability to choose red and 25 over 51 to choose black. Our third choice takes it down one more. Notice we now have 50 cards in the deck, and just depending on where the branches are is what we choose. If we've already chosen 2 red, then we're down to 24. If we haven't chosen any, but the black is still at 26. If we had a red and then a black and then a red, it's 25 out of 50 for the red and 25 for the black, and so forth. So you can see how that works depending on what card you're assuming you pulled previously. And you've got the arrows there marking where we have exactly 2 reds and 1 black. They're marking the branches there. There's 3 of them. Now, what we're going to do here is, let's see, it says here we need a probability true 3 stages. We just saw that. And we saw that it's exactly 2 cards for the arrows. We're going to multiply the probabilities along the branches, and then we're going to add it up because it can happen one of those 3 ways, which is an OR, which means we're going to add. So we end up with 0.382. Okay, independent events. Events are independent when the result of one event does not have any impact on the result of another. Mathematically, an independent event is happens when the probability of F given E is the same as the probability of F, or the probability of E given F is the same as the probability of E. For example, flipping a coin multiple times, drawing a card, then replacing it in the deck before drawing another card, or rolling a die. The idea is that the fact that one event has already occurred, it doesn't affect the probability of the second event, which is why we say the probability of F given E is the same as the probability of F. The fact that E has happened doesn't have any impact on it. And we can use this to determine if two events are dependent or independent. If you figure out the probability of F given E and it doesn't match the probability of F, then they're not independent. So it's just a way of checking. The product rule for independent events says that if you have 2 independent events, then the probability of their intersection is the probability of their individual events happening multiplied together. And we've actually already worked with this a little bit. Okay, here we have an example involving a 2-step process. Both steps are assumed to be independent. Would you read over the question, give it a try, pause the recording while you're doing that, and resume the recording to check your answer. Since they're independent events, we can just multiply the probabilities together. Now remember, you need to change the percentages to a decimal. And when we do that, we get 0.9457 probability that both components will be satisfactory. It's really easy to confuse independent and disjoint. Independent events can happen at the same time or within the same set of circumstances, but the outcome of one does not affect the outcome of the other. Disjoint events cannot happen at the same time. So the outcome of one actually affects the other because if one thing happens, the other can't. For example, getting an A in English and getting an A in science may be independent. They can happen at the same time. It's possible that one does not affect the other. There could be underlying things affecting both, but in all likelihood, they're probably independent. However, getting an A in history and getting a C in history are disjoint because once one has occurred, the probability of the other happening drops to 0. And here's another example. Read over the problem, give it a try, pause the recording, and then resume to check your answer. Okay, so E is going to be the event that the firm is dedicated to real estate rentals or leasing F is going to represent the event that the firm is a partnership. We want to determine the probability of, if the probability of E given F equals the probability of E, or the other way around. It doesn't really matter which way. We know that the probability that they're dedicated to real estate rentals or leasing is 0.241. We know that the probability of a partnership is 0.352. We know the probability of the union is 0.424. Now we do need to know the intersection, so we use our addition rule and find that that's 0.169. So the probability of E given F is the intersection over the probability of F, which is 0.169 over 0.352, which is 0.480. Well, that's not the same as the probability of E. We can also do it the other way around. The probability of F given E is the intersection of the two over the probability of E, which is 0.701, and that is not the probability of F. So because the probabilities don't match up, the two events are not independent. All right, the rest of this is some extra practice. Give these a try, pause the recording as you do them, and resume to check your answer. Continue this way to the end of the recording.